In this lecture, we're going to look at constrained optimization somewhat more. We're going to look at the Karush-Kuhn-Tucker conditions, shadow prices, and dynamic Lagrangians. Now, you might wonder why I don't use the camera. Well, I've tried to use the camera, but the problem is that the files get too big and I have trouble loading them between various devices. So let's start with the Karush-Kuhn-Tucker conditions, which I'll call KKT conditions. And we saw earlier what the complementary slackness conditions were. And we see here that this basically is the complementary slackness condition that we had previously. And to that we added this one. So basically what it says is the following. If the amount of x we have, it either has to be 0 or this value here, the partial derivative of the Lagrangian with respect to xj, any xj, is equal to 0. And the same thing when we take a look at lambda, we find that either lambda is 0 or the partial of the Lagrangian with respect to lambda is 0, or sometimes in odd cases both are 0, and those are the complementary slackness conditions. So let's look at an example of how the KKT conditions apply. So let's say we're maximizing this function 8x1 squared plus 2x2 squared, and we got a constraint that x1 squared plus x2 squared is less than or equal to 9, and that importantly these x1 and x2 have to be greater than or equal to 0. So in other words, they have to be non-negative. It can't just be positive. Positive means that they're only greater than 0 and they cannot take on the value 0. So we form this Lagrangian here, which is 8x squared plus 2x squared, which is the objective, plus lambda. Notice I've moved that 9 here to the side to the left, and then rearrange that so we get 9 minus x1 squared minus x2 squared is given our constraint, and that means we got a plus sign down here. All right, so the KKT conditions are as follows. That the partial of L, the Lagrangian, with respect to x1 is equal to the first derivative of the objective function, which is 16x1, minus the derivative here where we have the lambda minus x1 squared, so we'd have a 2 lambda times x1, and it has to be less than or equal to 0. x1 has to be greater than or equal to 0, and then we notice that the x1 times that partial of L with respect to x1 has to be equal to 0 as well. And the same thing applies with the second variable in the function x2. We get that the 4x2 minus 2 lambda x2 is less than or equal to 0. x2 has to be greater than or equal to 0, and this condition, this complementary slackness condition, has to apply as well. And finally we take the partial with respect to lambda, and we end up with this here, which is the constraint again. It has to be greater than or equal to 0. Lambda has to be greater than or equal to 0. And again, we have this complementary slackness condition, all right, for lambda now. Note the directions of the inequalities versus for x versus lambda. So here, lambda is greater than or equal to 0, and for the x's, derivative of Lagrangian with respect to either one of the dependent variables has to be less than or equal to 0. And here, with respect to lambda, it has to be greater than or equal to 0. So now, what we have to do to find the KKT, the Karush-Kuhn-Tucker conditions, we got to examine every single case. So we start with A, where the partial with respect to x1 of the partial of Lagrangian with respect to x1 has to equal 0 if x1 star, where the star refers to the optimal, is greater than 0. Same thing with partial of Lagrangian with respect to x2, and again this is if x2 is greater than 0, the optimal, and again for partial of the Lagrangian with respect to lambda, where lambda star has to be greater than 0. If, on the other hand, we have this condition that's less than or equal to 0, if x1 is equal to 0, and the same thing for x2, and for this one here, we've rearranged that. Okay, notice how I've rearranged that so that this greater than or equal to 0 sign is now a less than or equal to sign, because I've multiplied that through by -1. So now there are 2 to the power q plus p possible solution combinations, where q is the variables, we got 2, and p is the number of constraints, we have 1. So we have 2 plus 1, 2 to the power 3 is 8 possible solutions. If we look at these, then we find that if we have all these possibilities, for case 1, everything is 0, x1, x2, and lambda. Then we change this lambda first, then we change the x2, leaving the other two 0, then the x1 is greater than 0, so it's positive, and the other two are 0, and we look at all those possible combinations, of which there are 8. All right, and these are the Kuhn-Tucker conditions that they satisfy. They're given down here, down this column, all right, and they refer to conditions A, B, C, D, E, F. And now we're going to work through each case separately. So we have x1, x2, and lambda equals 0. Then what we have is that y up here, y is equal to 0. The constraints are satisfied. Check this constraint, it's satisfied, and we get a result. So this is a possible solution. For case 2, if lambda is greater than 0, it's not true that -9 is equal to 0. So if we go back here, so we have lambda 0, this condition, and these two are 0, pardon me. Lambda is greater than 0. Here lambda is greater than 0. This is the case we're looking at, not the one that I just mentioned. And notice that these two are 0. So this one is 0 and this one is 0. So -9 is not equal to 0. So of course that doesn't apply. So we do that for the other ones too. If x2 is chosen to be greater than 0 and lambda and x1 are 0, it's not true that for x2 equals 0 if x2 is greater than 0. And you can check these on your own. Just walk through them all. And you'll find that if x1 is equal to 0, then what we have is the following. Let's go back a minute. So we got x2, we've got that x1 is equal to 0 and the other ones are greater than 0. So we have x1 equals 0 and the others are greater than or equal to 0, or greater than 0, they're positive. So D, B, and C. So D, B, and C, so these three apply. x2 is 0, so this is 0. x1 equals 0 and x2 and lambda greater than 0. So x2 equals 0, x1 equals 0, that's this one here. If x1 is 0, then this holds, but these other two are these cases here. All right, lambda is a positive and x2 is positive. So let's look here. If x2 is positive, we could have some lambda, because lambda is not equal to 0, so this could hold. And likewise, this one is 0, so x2 squared is equal to 9, so x2 has to be 3. All right, remember, it can't be -3 because these all have to be positive. So in that case, we get x2 is 3, as I mentioned, since x1 is 0. And if we go back to the other constraint, we get this result, so lambda is equal to 2. So constraint D is satisfied. So then we plug in the value of x2 into this objective function at the top of the screen, and we get 8 times 0 plus 2 times 3 squared, which is equal to 18. We do the same thing if x2 is 0, then we find that x1 squared plus x2 squared minus 9 equals 0, and in this case what we have is that x1 is 3, since x2 is 0. Again, we go to the next constraint, E, and we find that lambda is 8. constraint E is satisfied, y equals 8 times 3 squared plus 2 times 0 squared. We get 72 as the objective. So we've got 3 solutions so far, and this one where lambda is 0, x1 equals x2 is 0, that one implies that y equals 0. The solution in this case, in the last case where they're all greater than 0, lies on the boundary. The constraint is binding since lambda is greater than 0, solving A, B, and C simultaneously. So in this case, we get these 3 applying for that last condition. So this is the number 8. We see that for number 8, we get that lambda is 8, and we also get that lambda is 2, but that's an inconsistency. So this solution doesn't really apply, although the constraint is binding. So case 6 yields the optimal solution here, 72. That's our optimal solution. Notice that the shadow price is 8, so that increasing the right-hand side of the constraint from 9 to 10 will increase the objective value by 8 units. So that's what we mean by a shadow price. Because lambda is 8 here, that means that if we increase that right-hand side by 1 unit from 9 till 10, we get an increase in the objective function of 8 units. So if that were the case, then this would be 80. So these KKT conditions will always yield a solution to an appropriately specified, in this case it was a nonlinear programming problem, but the search for all possible cases makes it increasingly difficult to find a solution as the number of decision variables and constraints increases. Suppose we have Q equals 3, so 3 variables and 2 constraints, so P equals 2. The number of cases to be considered has to be 32. If P equals 3, then the number of cases is equal to 64. And you see that they rise very quickly, and when you have 32 or 64 cases to consider, it's difficult enough to do it with when you have 8, let alone 32 or 68, and then you have what we call the curse of dimensionality. All right, let's look some more at these shadow prices. All right, so let's consider a game rancher who's selling meat to a local restaurant. All right, this is something that we've encountered with one of my PhD students from Kenya at one point, that they had ranchers around Nairobi. They put up a fence around their property, and they had wildlife inside the fence, and they would cull the wildlife and sell the products to the restaurants. So the rancher's objective, of course, is to maximize the discounted present value of income from harvesting wildlife species over time, subject to the constraint that the wildlife stock is a function of growth and harvest. So, of course, if a rancher were to cull some animals and sell them to the restaurant, then those animals would not produce any offspring. So you have to take that into account as a rancher. So the rancher doesn't want to get rid of all of his animals forthwith, because that would be too expensive. So over a period of time, the rancher will cull animals in a way that he has enough animals for the next period, depending on prices and so on, in order to maximize the discounted net present value. All right, so suppose that the rancher is coming to the very last period. He's going to retire, or maybe he's selling the ranch or something like that, or a developer is coming along and going to take the property away. What is he going to do? Suppose that we find that the rancher culls all of the animals. Then what we would expect is that X is greater than 0, and the shadow price would be positive. Call it SDP for shadow price. It would be positive. In other words, if the rancher if there was still another animal out there, the rancher would try and cull that animal as well. However, if we find that the rancher is not taking all of the animals, so in other words, there are some animals left at the end of that final time period, what is that telling us? Well, it's telling us that the cost of harvesting an additional animal is greater than the revenue that they're going to get from it. So in other words, the shadow price is going to be 0. So that's what we mean when we discuss this this whole deal about shadow prices. So if we have that the rancher finds that he takes all of the animals, then there's always a chance that we're right at that point where both the shadow price is 0 and the number of animals is 0. But generally, we would find that if the number of animals is 0, so he takes all of the animals, that would imply that the last animal he took, he gained more revenue from the animal than it cost him to cull the animal. So the marginal revenue would be greater than the marginal cost. If, however, we find that there's animals left over, which are then the developer would have to get rid of them, or just tear the fence down and let them go. But the point is that if there were animals left over, it would not pay the rancher to take those animals. There'd be excess animals, so the marginal cost would be greater than marginal revenue, and the shadow price in that case would be 0. The same thing we find if there's unemployment, then the shadow price of labor would be 0. Let's consider this game farming example a bit further. So we have that the rancher is selling meat to local restaurants. The state variable, we refer to it as the state variable, is the stock of wildlife. In other words, we cannot affect that variable except through our decision variable, or our control variable as we call it, and that is how much of the animals, how many animals do we harvest in each period or year, and we denote that with an H. We assume a time horizon of T years, and no harvest is allowed in that final year. So in other words, the farmer would, or the rancher would, take all of the animals in the year prior to big T, so the year T minus 1, and we have a discount rate. We're going to be, our discount factor, and we're taking that discount factor as just simply 1 over 1 plus R, where R is the rancher's discount rate. So we can set this problem up as follows, where we maximize the revenue, discounted revenue. We discount that by this factor here. So in other words, if beta T is 0, then this would be a 1, and we would discount that as follows, and we do that over the entire time period up to big T minus 1, and at big T minus 1 we get some return on salvage. The salvage value depends on how many animals we keep. The constraint here is a little different than what you're used to because it's a dynamic constraint. It tells us that the difference between the population tomorrow and that today is given by the growth of population, which depends on the number of animals currently in existence, minus what we harvest today. We assume that x naught equals x bar, so in other words, in time period t equals 0, we have this number of animals. The net return from harvesting wildlife is given by this function here. The growth rate of wildlife is given by that function, and the salvage value by this. Now, to make things tractable, let's just assume that t is 3, so in other words, we have 4 periods, the current one, and then two more years of harvest. So we harvest today in the current period, next year and the year after, and then in the 4th year we basically sell the ranch off. And how much we get depends on how many animals there are on the ranch at that time. So a little bit different than what I'd mentioned a little earlier. So now we write the Lagrangian like this, from t equals 0 to 2, because there's 2 years of harvest. So what we have in square brackets there is the discounted return to the rancher from sales to the restaurants. And then we have this factor here. This is your salvage in that 3rd period, so the final year. And this is the 1st period, all right, where we're told that x bar is the number of animals that we had when we bought the ranch or that we put in place ourselves. And notice again that we've taken the right-hand side and put it on the left here so that we get a positive value there. And then we have this way of writing. Notice that it's a t plus 1 in both here and here because it's the future. So this basically is the future value, shadow price, shadow value, future shadow value. and this is the growth function minus the harvest, and then we had that left-hand side, which we've now moved to the right-hand side. So we can rewrite this in its entirety as the discounted revenues plus the constraint of how many animals we have in the first period, plus a discount 1 over 1 plus r times this lambda 1. All right, so lambda 0 is a particular Lagrange multiplier, lambda 1 is another Lagrange multiplier, and then we look at the growth in the stock in the first period minus what we harvest in that period, and that gives us the change from period 0 to period 1. We do the same thing for 2, and we get a harvest in the period 1, or the second period, and again the change over that going from 1 to... And finally the third period, where we're harvesting, and we get that change in population of the animals. And finally we have this salvage term here. All right, now we're going to take first order conditions. Now the first set of first order conditions relate to the partial derivatives of the control variable, which is harvest. So we have to look at the 3 time periods in which we harvest. The first time period is this one here, where we look at the partial of the Lagrangian with respect to HO, and if we go back one slide, we see that H appears here and it appears here. So it appears twice. So we're going to have that beta 0, which is essentially 1. This is equal to 1. And that's times the partial of the return function with respect to the harvest in period 0. So that's the amount of income we earn from that, or net income from harvesting that many animals in the first period, minus beta 1 times alpha 1, where alpha 1 is the shadow price. It's the value of an animal retained this period so that it can grow into the next period via the growth function, and that has to equal 0. In the second period, which we denote period 1, we have a discount factor. Now it comes into play. We're discounting by one period the sales that occur, the net revenue that occurs here, and we also have that we take into account if we had not harvested the last marginal animal, what its value would have been had we kept it to the next period. And we do the same thing in that third period, and then notice that we have no harvest occurring in the third period because that's our final period where we actually sold the property. So now we look at the co-state equations. Now we're looking at differentiating the Lagrange function with respect to each period over time as well. So if we go back to the original, now notice here that no, we want the Lagrange function, pardon me, I was going the wrong way. Here we go, this one. All right, so notice when we take, let's just pick one. Suppose we want to take the partial of period 1, x1. So then we have a beta to the power 1. So we have beta there. We have an xt that occurs here, so we got a partial of r with respect to x1. There's no x1 here. There's only an x0. There's an x1 here. All right, so we have a beta 1, lambda 1, but it's a negative sign because of the negative sign here. And notice that we also have this beta 2, lambda 2, because we have an x1 here. And that often confuses students, the fact that we have an x1 in this period and an x1 in this period. Okay, and we can do the same thing with regards to x2. We have one here, and we have one here, and of course we have one up here again. So we have to keep that in mind when we do that, and we when we do that, we get these results here. You can see that, and we can finally take the derivatives with respect to lambda, and in that case we recover all of the individual constraints. And notice that we also take a derivative with respect to lambda 3, because there is that constraint here that still holds as we go into that third and final period. Now we can summarize the foregoing conditions by the following equations. The partial of the Lagrangian with respect to ht is equal to 0. That implies that we get the left-hand side, the partial of the net returns with respect to the harvest at any given period of time, is equal to beta times that shadow price, lambda t plus 1, and we're discounting that price by that beta. We do the same thing. We can rearrange the second set of equations to beta lambda t plus 1 minus lambda t, and we get that negative with the expression in square brackets, and I won't try to explain that, but it's some kind of a arbitrage condition. And the third condition that we have is the constraints again, the growth function essentially. That says that the change from one year to the next is equal to growth minus harvest. We call the first set of equations the maximum principle. The second set of equations is referred to as the co-state equation, and the third one as the state equation, because it tells us how xt changes over time. The fourth and fifth equations are basically endpoint conditions. The starting point condition, x0 equals lambda x bar, and then lambda t is the shadow price in the final period, which is s, the first derivative of the salvage value with respect to the amount of animals still available in period t, capital T. And they're referred to as the transversality conditions. Now, I would not worry about what these particular terms mean, all right, because that is what we will do in 351. Now, we can look at a particular other example, the mine problem, just for fun. So we determine the problem. The mine problem is this: determine the optimal production schedule for extracting ore from a mine for periods t 0, 1 to 9 for a mine that is to be shut down and abandoned in the 10th period. We assume the output price is equal to 1 and that the extraction costs are a function of output extraction, and we take the square of output extraction divided by xt. So as xt falls, the cost goes up, and as you increase the amount of ore you remove in any period of time, any year, then the cost goes up as well in a quadratic. We assume no discounting just for convenience, and we define net revenue. Let me see if I can find my cursor here. Net revenue, or profit rather, as price times the amount of ore extracted in the period minus the cost, y squared over x squared, and we can, because price is 1, we can rewrite this as follows. And what's key here is this little thing there, because it makes everything tractable without having to go to some kind of a mathematical programming package such as GAMS. And of course we have, this is our equivalent of the growth function that we saw previously, and what we find here is that the change in the amount of ore that's in the mine is equal to minus y, the extraction in any given period, and we assume that we start with 1,000 units of ore. So how do we solve this? Well, we form our Lagrangian for the mine problem as usual, and again a key figure here, or key value here, is the choice that we make with regards to that little y over x t. So here's our Lagrangian. This is the objective function again, and then again these constraints, which are, we got a t plus 1 here, and because of that t plus 1 there. So the first order conditions are, again, this number 1 is our maximum principle, where we take the partial of the Lagrangian with respect to the control variable, how much ore we remove from the mine in any given period of time, and we find that equation and set it equal to 0. We do the same thing with the amount of ore left in the mine at any given period, and we set that equal to 0. And finally, we take the partial of the Lagrangian with respect to lambda t plus 1, and we end up with this third equation here, which we hold. Now notice that these equations hold for different time periods. This one holds for periods 0 to 9, this one from 1 to 9, and this one from 0 to 9. So this gives us 10, this gives us 10, and this gives us 9 as well. So with x0 equal to 1,000 and lambda 10, we set equal to 0. So in other words, recalling our discussion above, we take all the ore out until that lambda is 0. So in other words, we're saying that we can't take all of the ore out, and we'll see that in a minute. So the first order conditions represent a system of 31 equations and 31 unknowns. T is for t 0, 1 to 9, that's 10. Xt is for 0, 1 to 10, and I think I got that wrong up here. The xt should be, this should be a 10. And then we have the other one is for lambda t, that goes from 1 to 10 as well. So we end up with 31 equations and 31 unknowns. Now the key, as I mentioned before, was this possibility here, setting zt equal to yt over xt. So we rewrite equation 1 with the zt, so we get zt equals 1/2 1 minus lambda t plus 1. Since lambda 10 is 0, we can find z9 being 1/2 using this equation, and then rewrite equation 2 as lambda t zt squared plus lambda t plus 1. So if we're given that lambda 10 is 0, we can find z9 to be 0.5 from equation 1a rather. Then lambda 9 is given by equation 2a, where z9 is squared, so 0.5 squared is 0.25, and lambda t plus 1 for 10 here is 0. Then we can find z8 from equation 1a again, lambda 8 from equation 2a, and so on down. So we basically end up with determining this column first, followed by this column. Then we reverse this column. We reverse these numbers in the first 3 columns, so that instead of going from 0 here up to 10, okay, it's going to go from 0 down to 10. So in other words, this 0, these 2 values here are simply given by these 2 values here, and so on as we move up in these 2 columns along here. And from that we can use the result that y over x is z, and from that we can decompose z into y and an x. And the important thing to realize here is that as we go down in the 10th period, there's no harvest. It doesn't pay to harvest, which is why the lambda is 0. And we notice that 50 units of the 1,000 that we started with are still left in the mine. So that is our complementary slackness condition there. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.